So how are we going to solve this? So one option would be to find a common denominator for these two and combine them. Another thing that you can look for is, which by the way, the advantage of that would be seeing if you could set then the numerator equals 0, denominator equals 0, and you could find the critical points not only where f prime is equal to 0, but also where f prime is undefined. But look in this case to see if there's a reason that you would know for a fact that the denominators are never going to be 0. So in this case, you know, if my common denominator would be 2 square root 25 minus x squared. So my question is, could I just multiply this equation by 2 times square root of 25 minus x squared, thereby clearing out all my fractions? That would be ideal, but I would need to know some reason why this expression cannot equal 0. Well, there is a reason why this cannot equal 0. The only way this could equal 0 is if x squared is 25. The only way x squared could equal 25 is if x equals 5. Well, if x equals 5 and the hypotenuse is 5, you wouldn't have a triangle anymore. Therefore, the x cannot be 5. 25 minus x squared cannot be 0. Therefore, we can multiply both sides of the equation by 2 square root 25 minus x squared. So ideally, we like to multiply both sides of an equation by a least common multiple, but only if you know that that least common multiple cannot be 0. So be careful, because sometimes it might be. All right, so when I do that, the 2 and the 2 are going to cancel. Square root 25 minus x squared times square root 25 minus x squared is just going to be 25 minus x squared. The 2 square root 25 minus x squared will cancel with this whole denominator, so I'll have minus x squared. Then I have equals 0. So I'm going to have 2x squared equals 25, x squared equals 25 over 2, x equals plus or minus square root 25 over 2. But since x again represents the length of a side of a triangle, x has to equal positive square root 25 over 2, also known as 5 over square root 2, also known as 5 square root 2 over 2. Now, by the way, if you know your 45 triangles really well, which you should, then when you see this number, 5 over square root 2, and you know you've got a right triangle, and the hypotenuse is 5, and one leg is 5 divided by square root 2, then the other one's also 5 square root 2, and it's a 45, 90 triangle, as we suspected from the beginning. So that could be using your geometric knowledge to already know that this is a maximum, and already know, well, we don't know that it's a maximum just from the geometry, but we do know that the other side is also 5 square root of 2, 5 over square root of 2, and we already know it's a 45, 90 triangle. Okay, but is it really the maximum volume area, or could that be the minimum area? Maybe that's the minimum area. So here's how we're going to find out. We're going to go to a derivative test. Now, here's a good example of a case where I really do not want to use the second derivative test. Do you really want to find the derivative of that? I don't. Now, it's going to be hard enough to use first derivative test, but not impossible, and not as hard, I think, as finding the second derivative. So I'll show you how that goes. In order to do first derivative test, we are going to need to get a common denominator for these two. So when I look at my a prime, which is equal to square root 25 minus x squared over 2 minus x squared over 2 square root 25 minus x squared. All right, what I can do is just get a common denominator for these by multiplying the top and bottom by square root 25 minus x squared on this fraction. All right, and then you're going to start to see things look very similar to what we had up here, because when I multiply these two together, I get just 25 minus x squared, and then I'm going to have the minus x squared, and then my denominator, this is the part that's different from up here, my denominator is 2 square root 25 minus x squared. But notice how the numerator is just the same as our equation here. That would have been another way to solve this equation. All right, so and I can simplify that a little bit more by saying that equals 25 minus 2x squared over 2 square root 25 minus x squared. Okay, now that doesn't look a whole lot better, but it is, and here's why. So I'm going to use first derivative test on x equals, now I'm going to leave it in this form, 5 over square root 2. You're going to see why that's useful. Actually, even going back to square root 25 over 2 will be pretty useful to us, I think. All right, so what happens when x is less than 5 over square root 2, and what happens when x is greater than 5 over square root 2. What happens to my derivative a prime, which is 25 minus 2x squared over 2 square root 25 minus x squared in each case. All right, so one thing I'm going to notice is a square root is always positive. So this denominator is always positive in both cases. So that's nice. Now, if I take the square root of 25 over 2 and I square it, I'm going to get 25 over 2. And then if I multiply by 2, I'm going to get 25. So if I took a number less than that, I'm going to be taking 25 and subtracting a number that is less than 25. So I'm going to get a positive number. So a prime is positive when x is less than 5 square root of 2. Likewise, when x is greater than 5 square root of 2, I'm going to have a number that's slightly greater than square root 25 over 2. Square root 25 over 2, when I square it, is going to be 25 over 2 multiplied by 2, 25 minus 25, except this is actually a number slightly larger than 25, so I'm going to have a negative for a prime. All right, so now I know that the area has a max at x equals 5 square root 2 over 2 because a prime changes positive to negative. So now I know that's a max. So we'll finish this up in the next video.